Hey guys, welcome back. We are now at day 10, so after today we will be halfway done with our e-learning, so hopefully you guys are hanging in there. Real quick before we get started, make sure you guys are checking in on grades, make sure you're asking questions if you have them, because the end of the year is quickly approaching. Like I just said, we only have 10 more days of distance learning, and that's going to constitute the rest of the year, so make sure you guys are on top of everything. Most of you have done a really good job at staying in touch, keeping contact, asking questions if you have them. So thank you for that. For those of you that are missing stuff or um, need to get your grade up a little bit, make sure you're checking your grades. I'm going to start emailing people. I'm going to start calling parents and stuff like that. So just make sure you're on top of it. But anyway, so we're nearing the end. We're getting close to all of the stuff that I want to talk about. We went over transcription translation the last couple weeks, and hopefully that went fine. What I'd like to do now is we're going to move on to mutations this week. We're going to talk about what those are and the different types. And then after that, we're going to get into gene regulation, how you can turn certain genes on and off. And that will usually that takes us up to where the end of the year would be. I might have to do a couple or a little bit of adjusting because normally we'd have finals week and review week and all that stuff. So I might have to shift some stuff around for timing since we're not going to be doing finals. We might spend a little bit more time on some stuff than I normally would. But anyway, before I go too much with the rambling, let's just go ahead and get into it. So this week we're looking at mutations. This should be, at least in my opinion, easier than what we have been doing with transcription and translation, which might be relieving to some of you if you struggled with that. Mutations are fairly simple. It's mostly definitional, like knowing what the types of mutations are and how they change the DNA. So that's what we're going to be practicing today, is just identifying different types of mutations. So first of all, what is a mutation? It's a word that you have probably heard a lot just colloquially in movies and TV shows and stuff like that. You know, you've got your X-Men, you've got your Teenage Mutant Ninja Turtles, but that might be, well, they still make variations of that now. It's kind of dated, but they keep reiterating it. But anyway, so what is mutation? A mutation is any random change in the DNA, any change at all. Most of the time we associate it with drastic visual changes, whether it's like, you know, like the good change, like gaining superpowers in the movies and all that stuff, or even like the bad change where they turn into some mutant monster thing like that. We normally associate with like either a really good change or a really bad change, but it doesn't have to be either of those. It could be anything at all. It could be very, very minor. It might not even do anything, but if it's a change in the DNA, then it's considered a mutation. You have mutations in your DNA right now. You aren't expressing them probably, hopefully, but your DNA is mutating because you have so much of it, and just it's impossible to make sure that it stays correct all the time in every single cell of your body. So most of the time mutations don't do anything, but we're going to get into the different types today and what happens when they do change. So 3 possible outcomes. Either it can be a good change, it causes a mutation that adds new function that was not previously seen before. A good example of this is, I forget at what point in our history, but several 100,000 years ago, some of the earliest humans developed a mutation that allows them to digest lactose after infancy. And if you know that term, lactose is the sugar that's found in milk. Most organisms don't drink milk past the time that they are a baby. You will not give milk to a fully grown cow or pig or dog or stuff like that. They don't drink milk. They can't digest it past a certain point. However, humans are unique in that aspect, and maybe some other organisms, because I know you give cats milk, but I don't know. There was a mutation that allowed them, or allowed us, I don't know if I'm saying them, to digest lactose past infancy. There's another one, which this might be kind of a give and take, where some people are born with a random mutation that makes their bones extremely dense, and because of that, they are less likely to break bones, and their bones are very durable. The trade-off being that I think it makes them heavier, so they can't, or more dense, so they can't swim, or at least they have a harder time swimming. I don't know. You'll have to look into it. I might be making that up. That sounds kind of fairy tale-ish, but either way. It can be bad. A bad change. This is far more common, which would make sense, because if you imagine you have this instruction booklet that has taken literally hundreds of thousands of years to be put together, and it's all put together in a precise way to allow for a specific outcome. If you were going to go in and change a single line of that, you're going to mess everything else up. If you've been building a tower for, let's say, 100,000 years, and you have the foundation, you've been adding to the foundation as you go up, and you're going further and further up towards the top, if you change anything along the way, chances are that tower is going to come crashing down. This is what happens when you get organisms that are missing limbs, organisms that have not like too many eyes, not enough eyes. The two-headed pig in my cabinet, for all these, all of you that were very interested in the two-headed pig, that's an example of a detrimental mutation. And then the last type is no change at all. And this is the one, again, that most people don't really acknowledge because there's no change. I think I've mentioned this in class before, but a lot of your DNA actually doesn't do anything. A lot of DNA is leftover junk from our evolutionary lineage. They were genes that may have served some function at some point, but got turned off, but they're just still part of the DNA code. They just haven't been removed yet, if they will be removed at all. So a lot of DNA doesn't actually do anything, or at least anything that we can tell. If there's a mutation in this DNA that doesn't code for anything, then most of the time there's no physical change. There's still a lot of study into what this DNA does, if anything, so maybe there will be some change in the future that we find, but for the most part, no change at all. But yeah. So, we're going to go over the different types, and I'll try to speed this up because I'm already taking longer than I should. Types of mutations. Substitution mutation, a lot of these are self-explanatory. They sound exactly like what the name is, so they'll be pretty easy to remember, I think. Substitution is exactly what it sounds like. You're just substituting out one letter for another letter. So if you remember the DNA code, you got A's, G's, T's, and C's in some random variation like we looked at last week with transcription and translation. It could be AGGG, AGGG. It could be AGG, it's only 3 letters long, ATT, TCG, whatever it may be. So all you're doing with the substitution mutation is you're swapping out one letter for another letter. Overall, the total length of the code is still the same, but something in there has changed. So yesterday, I used, so for my examples, I used actual sentences, so it makes more sense as opposed to like, because if you're reading just a DNA code, you're not going to understand what, no one just reads DNA and is like, oh yeah, I understand what that means without looking at the amino acid chart. So I used sentences to make it more obvious. So yesterday I went to the store to get some apples. Yesterday I went to the shore to get some apples. I only changed one letter. Each sentence has the same number of letters. However, this sentence and this sentence have very different meanings. You're going to interpret them different. That won't always be the case, but I wanted to make it obvious for this example. So, just swapping out a letter. Frame shift mutation. This one is a little bit more confusing because it's not something, the title doesn't really tell you that much about it unless you have experience with it. So what happens with this, with a frame shift? Since your DNA is read 3 codes at a time, like we were doing all last week when you were looking at your DNA sequence, I always grouped them up in 3s. If you add a letter or take a letter out, you then have to shift everything else over because every word has to be 3 letters long. If you were typing a paper and you accidentally made a typo and you wrote a word that had an extra letter in it, it would just be that word with an extra letter in it, and it would just have 1 extra letter. However, with DNA, the way that would work is that would push everything else over a space. So imagine you were typing a paper and you accidentally add a letter that's not supposed to be there. Instead of just messing up that word, it messes up every word past that word because now all the letters get shifted over a space. So I'll show you what I mean. It'll make more sense when I show you some examples. 3 ways you can get a frame shift mutation: insert a base pair, delete a base pair, or duplicate a base pair. First one's insertion. You're adding a letter into the sentence somewhere randomly. So here's my example. The dog ran and the cat ran too. My mutation, I added a T right here in the sentence. So between the A and the N of ran, I added a T. Again, normally if you were writing a paper as a person, as a human being, it would just mess up your sentence. It would say R-A-T-N and then and the cat ran too. But since DNA has to be read 3 letters at a time, all these letters get shifted over 1. So the T that was here got moved to here where the A is. So N, the N goes here, A, N, D. Notice that the letters still go in the same sequence, but now that the spacing's off, it doesn't make any sense. So the words are still there, and the cat, but since it's framed a particular way, when your eyes read it, it doesn't make any sense. The whole sentence got changed because of how I added 1 base pair. So dog, rat, nan, dith, eka, it's like I'm having a stroke. So yeah, hopefully that makes sense. Normally if we were in a classroom setting, you guys would have a chance to ask questions, but this is something that I think there might be some confusion on just because of the limitation on how we can communicate with this. So please email me if you have any questions about this. But either way, we'll keep moving. Duplication is exactly what it sounds like. You're just copying a letter and doing it twice. Again, another common typo that you would probably have just in English class where you're typing something and you accidentally hit the key twice and one of your words has the same letter in it too many times. The dog ran and the cat ran too. The dog ran and the accidentally duplicated the T. And everything else has to get shifted over to compensate. So the H gets moved, the E gets moved, so on and so forth. You get the idea. Everything past my mutation got messed up, so now the rest of the sentence doesn't make any sense. And then deletion is exactly what it sounds like, so I'll make it quick. You're just deleting a letter somewhere in here, and then it shifts everything else over to compensate. So if I accidentally delete the T in the, everything else has to move over to compensate. So the H goes where the T was, the E goes where the H was, C goes over, A goes over, all that stuff. Everything past my mutation got messed up, and you'll notice that my frame now has one less letter than it should. This one is letter short. That's a really easy way to identify if you have a frame shift mutation, is if you look at the very end of your sequence and there is an uneven number of letters. So either you have one less, so there's only two in a pairing, or if it's added, you have one extra letter, so there's one hanging off on the end there. That's a really easy way to tell if it's a frame shift mutation. If it's the same length and there's no loose ends, then it's probably just substitution. Okay, now we're gonna get into the actual like cause or the changes in function. So the rest of these we're just talking about how did you change the DNA code, what's different about the way the DNA is being read. These types of mutations are descriptive. They're talking about what change did that cause in how the DNA produces proteins. So the first one, silent mutation. Silent mutation means that there is no change. Essentially, there's some change in the DNA, but it didn't do anything substantial. There's a couple ways this can happen. Again, sorry, I'm blanking. So yeah, again, if it's in a sequence of DNA that doesn't code for anything, if it's junk DNA, then obviously that's not going to cause a change. But even if it is is part of a sequence that does code for something, if you noticed last week when we were doing our translation things, there were different codes that coded for the same thing. Let me see if I can scroll. So yeah, here. Notice how serine, all 4 of these code for serine. So even if you have a mutation that causes UUU to go to UUC, so we changed the letter, there's been a mutation. However, they both code for the same thing, so it's essentially it's essentially there was no change. So same idea. So my example here was the boy jumped off the rock versus the boy hopped off the rock. They're synonyms. They mean essentially the same thing. It might give you a little bit different of an idea of what you're talking about in your head depending on how you interpret those words, but at the end of the day, they mean essentially the same thing. You're going to take it the same way. Missense mutation causes a change in how the DNA is expressed. So this is where you will actually see a change in the protein, which will cause a change in how your body reacts. These are the detrimental, most of the time, detrimental mutations. So for example, people who are lactose intolerant, there has been a mutation where the gene that codes for the enzyme that digests lactose no longer folds the right way, so it does not do the thing that it's supposed to do. Same thing here. It changes the interpretation. It changes what the outcome is. The boy jumped off the rock versus the boy fell off the rock. Jumped implies there was intent. Fell implies that it was an accident. Another example I would use would be like if you're making something, if you're cooking and you're following a recipe, silent mutation would be like the difference between using brown eggs versus white eggs. They're both chicken eggs. They're both going to make the thing taste the same, maybe slightly different depending on how discerning your palate is. But a missense mutation would be like it calls for like a cup of sugar and you accidentally add a cup of salt. That's going to ruin whatever it is that you're making. Very drastic change in whatever it is that you're making. So an example of this would be if we did UUU and instead it mutates to UUA. UUA codes for leucine. UUU codes for phenylalanine. These are hard to say. So that will cause a change in what the protein is. Nonsense mutation. There's your Office reference for all of you that care about The Office. I don't know. But anyway, a nonsense mutation means that the protein was stopped early. So you cut it off before it's done being produced. So going back to the recipe example, let's say you're halfway through making a cake and you've added half the ingredients and then someone says, all right, time's up, put it in the oven, we're good to go. Your cake's not going to come out right. Same idea here. If you stop the code early, the protein stops early, the protein is not going to do what it was supposed to do. So it's like stopping in the middle of a sentence. If I said the boy jumped off the rock, you immediately know, okay, we got to go help this boy if he's hurt. If I just said the boy jumped off and I left it there, you're going to have questions for me. You're like, what did he jump off of? Like, do we need to go help him? Like, is he okay? But yeah, so if it cuts off early, if it stops in the middle of coding, then that is a nonsense mutation. An example of this, there are only 3 sequences that will code for stop or stop codon, so it has to mutate to one of these 3 sequences. It either has to mutate to UAA, UAG, or UGA. Those are the only 3 sequences that will code for a stop codon. I put some practice things in here. I don't want to go through them right now for the sake of time. Plus, we're going to do more of this later on in the week. So if you want to look through these, I'm going to post this PowerPoint with the video like I always do. So look through these. For a lot of these, and this goes for tomorrow too, for a lot of these, there's more than one right answer. So as long as you explain yourself, you don't stress out about like, well, it could be this, but it could also be this. It's not like math class where there's only typically one correct answer. I don't want to bad talk math. But anyway, so we'll get into that more tomorrow. Today's more of just an introduction. So I'll post a Google form just asking questions that will tell me that you've watched this. So like, what's a silent mutation? What's a missense mutation? That kind of thing. It just lets me know that you guys are participating. So anyway, for the rest of the week, we're going to look at some examples. Tomorrow, I'm going to post some examples of mutations. You're going to have to tell me what type it is. So I'm going to change like a certain letter, and you'll have to tell me like, is this a nonsense? Is this a missense? Is this a frame shift? Whatever it may be. Hopefully, it's not too difficult. Hopefully, it's a little bit easier than what we did last week, but it kind of depends on how well this gets communicated virtually. As always, email me if you have questions. Please make sure you're checking grades. But so far, a lot of you guys are doing a great job with this. Thank you. I know this is a really unique experience, and this is something that has been very challenging for both students and teachers. So thank you guys for, sorry, there's construction going outside. Thank you guys for hanging in there. A lot of you have done very well with this, so thank you. I think that's all I have. Sorry if this was long. I tried to keep these a little bit short, but there was a lot to go through today. So let me know if you have questions, and I'll see you guys tomorrow.